Hello, everyone. Welcome to the VaNTAGE seminar. I hope you all had a very happy Thanksgiving. This is our last talk in this series on profinite groups and Gawa groups. And today in the VaNTAGE seminar, we're very happy to have Chirstian Maire, who will be speaking on Massey products in number fields. And Chirstian, is it all right if we record this talk?
Yeah, of course.
Oh, great. And everyone feel free to ask questions during the talk.
Yeah,
Okay,
yeah,
Chirstian.
yeah.
Chirstian, please go ahead.
Okay, so thank you very much for the invitation. It's a great honor for me to give a lecture in this context. And moreover, I'm very happy because I am the third on the short list in this topic. So the first speaker in the list was Michael Larsen. The second one was Ravi Ramakrishna, and I'm the third. And my lecture is in the spirit, in fact, of the lecture of Michael and Ravi. And it was more or less, so the result I will show you was more or less done in the same time as the result of done with Michael and Ravi in this lecture. In fact, I think we should start with the theorem of Scholz and Richard, because as told you, Ravi and also Michael, our result are in the spirit of this theorem. So we start with a number field Q. In fact, we start with number field Q. We start with a finite P group where P is odd. So this theorem is 1937. And the theorem states that there exists a Galois extension L over Q, okay, such that the Galois group of K L over K over Q, in fact, is isomorphic to G. And moreover, in fact, if we follow the proof of Scholz-Richard, we have some extra information. We have two information. First, we can guarantee that the extension L over Q is stemly ramified. Okay. But the second thing is that we have also some information about the set of ramification. So if I denote by S, the set of ramification, so I want to count the primes that in Q, primes that are ramified in L over Q. Then this set is, in fact, at most N, where N is, in fact, it's a log P of G, so meaning that the order of G is P to the N. In fact, if we follow the proof, we can have more. We can also have a size of the prime L, because the prime L are given by some by Chebotarev density theorem in some governing field. So we have some. It's relatively explicit in certain sense, the construction. And the proof. So of course, for P2, we know now it's a theorem. It's okay, theorem. But this is due to Shafarevich, where there was a mistake, a small mistake coming from group theory, but in fact, just after he claims the proof, he just say, okay, maybe there is a small mistake for the group theory part, for the two groups in my proof, but here is a way to solve the problem. And very recently, there is a very nice paper of Schmid, maybe it's paper in algebra and number theory, maybe 5 or 10 years ago, So it just explain very well how to solve the problem for two groups. So yeah, it's a beautiful paper of Schmidt. Solve exactly the problem for two groups. So the proof of Schultz-Richards, in fact, is a classical proof of a local global principle. So the proof is the application of local global principle. And it's also by induction, coming from the fact that a P group is solvable. And there is two main things in the proof. So the first one is to kill the Shafarevich group of the problem. So I will just recall a famous result of Kor and Shafarevich. So what is this result? So just a large situation, K is a number field. S is a set of finite pairs, a finite set, in fact, of prime of K. Of course, for P is 2, and there is also the story if we should include or not the infinite place. But okay, for me, okay, I just forget these situations that can be sometimes complicate the situation. I denote by Ks the maximal copy extension of K on ramified side S. I denote by JS the Galois group of this extension. So this is the Propy group. Okay. Oops. Okay, so there is so what we know about this Propy group. So the number of generator of the group, so the dimension over Fp of the H1 GS over Fp. So we know that it's connected related to the class group and the unit, no, only to the class, okay, related to the class group of K and the reclass group, in fact. And what is important is the number of relation, so the dimension over F over the H2. So this group is connected also to the class group, but it's strongly connected to the unit, in fact, of K. Okay, so there is the big question when we study the group GS is to understand the relation, and of course, so how to understand these relations, and you just look at the map of the H2 GS with coefficient in Fp. So for the next, I just forget the coefficient, and we are just looking for the map. What is the image of the map on the localization? Of course, you can just look at the absolute, the sum over all place in K, and where GV is the absolute Galois group of your completion, some P. But because since the extension case over Q over K is unramified outside S, in fact, the image outside S is trivial. So we just it's the same to look at the image in the sum over place in S, and we call the kernel the Shafarevich group, SHA2, in fact, KS. But here I forgot the K. Okay. Of course, when S contains SP, we have some information about this group. It's coming from a Poitou-Tate duality, but when we are in the same situation, this group is very mysterious. But we have the theorem of Kor and Shafarevich that give an upper bound of this group. So this is the theorem of Kor and Shafarevich, saying that, in fact, this group, in fact, inject in the B key S, where B key S is by definition the dual of V key S. Okay, I just mentioned after we just mentioned after what is this guy, to the dual of this group, where V key S It's just a set of elements of K star, such that how to describe this? So if we look at the ideal generated by alpha in the it's the p power of a certain ideal, so as a fraction ideal. And moreover, so this set of number was introduced by Ravi, but here we have a sum S. So we had an extra condition that the alpha is a p power in the local completion at S. So in fact, we have of course, so it's easy to see that we have the VKS is included in the VKMT set, which was defined by Ravi. So it's alpha in K such that alpha is p power. And we should see this guy, this set, as in fact a Galois extension because we have a duality here. So it's natural to consider this Galois extension. So you add the p root of the unity that would be by k prime. And then after that, you take k prime p square root of vk empty set, okay? So this guy is isomorphic to the bk empty set, okay? And now where is my bks? So bks in the middle. Oops, okay. Okay, so what is okay? Okay. So my VK is in the middle, and now it's easy to see that this guy, this subgroup is generated by the Frobenius of the place in S, okay? So here I assume, because I speak about Frobenius in this extension, so I assume that S doesn't intersect the periodic place, okay? Then in this case, I can speak about Frobenius. So the subgroup here is generated by the Frobenius. And then now it's easy to see that if you choose a place in S such that the Frobenius generated this extension, which is finite, this extension is finite. How to see that? So in this extension, it's just controlled by the class group and the unit because it was mentioned last 2 weeks ago by Ravi. So there is a natural map. So you send to the alpha, you send the class of your element A in the class group, so you arrive in the p torsion of the class group, and now the kernel is just the unit. So this extension is finite, it's generated more or less by the units and the generator of the class group. And if you take very well the place S, in fact, you are sure that the BKS is empty. And in fact, when S is well chosen, you obtain that the BKS is equal exactly to p power of k, and which implies that the Shafarevich group is trivial, in fact. Okay, so this is the first observation, and then it implies that when you study some element in the H2, in this case, they are just can be read as local elements. So this is very important in the proof of Chirstian. First, kill the Shafarevich group, and then the problem becomes a part of the problem becomes some local problem. This is the first thing. There is another observation I can mention at this level. And this remark is very important. In fact, it's important in the paper of with Ravi and also with Fargid and Michael Larsen. This is the following remark. So if you start with the fact that zeta p is not in the base field, so you have this situation. So you have a Galois group which is not trivial, and you take an element S here, which is not trivial. And now you add k prime vk, okay? And so if you start, if you take now sigma in this Galois extension, okay? So you have a natural Galois action coming from the pairing from Kummer's theory that the S sigma S minus 1 is a sigma to the power of S, theta S, where theta S is just the cyclotomic character. Yeah, zeta p, you fix zeta p, the pure root of the unity, theta S. So this is a cyclotomic character. Okay, and this observation may imply the following observation, that if imagine you start with an extension here, okay, K prime, also, you take another extension here coming by composition with this extension, okay? And now if you have this extension, which is not trivial, okay? And now if you say, okay, maybe is there some intersection between my extension here and this extension? Forget the P here. And the answer is no, okay? Okay, so it's very important in the story. So here you have equality. Okay. If this extension is not trivial, so it implies that you have equality here. And of course, sometimes if zeta p in the base field, okay, you can have some intersection. And this is the main problem. In fact, when you follow the strategy of Church-Richards, and our also strategy with Ravi, Farjid, and Michael, and also the strategy I will explain later, this is the main difficulty, that sometimes if zeta p in the base field, you can have some intersection at this level, and this is a problem. So when zeta p is not the base field, there is no intersection. So the intersection is trivial, and it makes the life easier. It's the main thing, in fact, the story. I will recall later this point in the proof. Okay, so we have also the question of the embedding problem. So the proof is by induction. So we start with this context. So we assume that we have an extension. Okay, so we start with extension, okay, with Galois group G, which is construct, okay. And so we want to, okay, so we have also in parallel an extension here of G by Z mod P, okay. And so the question is if we want to see if there exists an extension here such that the Galois group is G-T. So this is the question. So we start with given extension L of K of Galois group G, and we want to solve the embedding problem. So there is two cases. So, okay. So there is two cases. Okay. So one is easy, one is a little bit more complicated. So the case easy is when the extension split. So okay. Okay, so if this extension splits, so the problem is easy to solve. In fact, remember last 2 weeks ago, Ravi speak about a Gramunier result. In fact, we just apply a Gramunier, like a Gramunier result. So it means that in this case, GT is the direct product of G times Z mod P. Okay, and so you want to construct a Z mod P extension of K such that okay, this is different from L over K, so it's easy. But in fact, in the question of the embedding problem to in Church-Richards, we need a little bit more. We need some splitting condition. So it's a refinement of Gramunier result, but okay, just say okay. It's not easy to, not so difficult to solve with some splitting condition. So it's easy to solve. So the most interesting situation is when epsilon is not is not splitting. So in this case, my exact sequence can be associated to some element of the H2. So there is a non-zero element of H2 that characterizes this exact sequence. And there is a very well-known result that explain how we can be sure that we can construct the G tilde. So maybe I have to produce. Okay, so okay, imagine that S is a set identified by S, a set of prime, a set of ramified prime in my first extension, L over K. Okay, so in fact, you have a map here. And the question is there a map like this? Okay. Of course, maybe the set of ramification is not sufficient. Maybe we have to add some extra ramification. But imagine that, remember, so we have some, we start first with the SHA2 to the H2G, GS, and the local V in S. And the criteria says that, okay, we can lift, okay, so as a solution, if the inflation map of the epsilon in H2GS is 0. Okay. And so we see quickly the interest of this sequence here, because if we start with S, which is trivial, such that this guy is trivial, so you obtain that your epsilon is here, is living here, the inflation of epsilon is here, and in fact, to be sure that it's 0, it's sufficient to see that locally is 0, but locally 0, it means that there is no obstruction locally, okay? And so this is the next step in the proof. We assume that, there is no local obstruction to lift the local decomposition group. So if there is no local obstruction, we can lift. Okay, we can lift G to G tilde. Okay. Okay, this is the main thing. Now there is one thing which is important, because we want to continue this process, and now we are not sure that the new my new extension. So we obtain by induction this extension, okay, with G tilde. But now if we want to continue the process, we are not sure. Okay, imagine okay, second, okay, with this guy. Okay. So we are not sure that locally there is no obstruction here to lift to this extension. This is the main difficulty. And in fact, there is a story of the action of the H1 on the H2 that can solve the problem. In terms of Galois extension, means that imagine you suppose that you have an extension Z mod P. So where's my, okay. Okay, imagine you have a Z mod P, cyclic Z mod P extension F over K here. And now if you make the compositon here, okay, in fact, the group theory tells us that in the middle, if you take Z mod P in the middle here, you obtain another solution of your embedding problem. Maybe I can write this way. So the Galois extension here, Galois group of this extension over K is isomorphic. L not tilde is different from LF. Huh? You take in the middle is isomorphic to G tilde. Okay. In fact, this is the idea. So if you start, if you have a solution here, the idea is that if you do some compositon with some Z mod P extension, you obtain some new solution. And the hope is that maybe you have infinitely many new solutions, of course, but maybe in the set of this solution, you can have a solution that locally there is no obstruction to lift again your extension G tilde to G tilde tilde. This is the idea, okay? And how to solve this? In fact, there is a commutative diagram. It's a question, in fact, in class field theory. So there is a commutative diagram here. Okay. Oops. which is not so difficult to get, but it's the key of the proof, which is the following one. So you start with H1G, okay, a state n, a set of prime. Okay, and I take only 10 prime to simplify. And I use also, I take another extra prime, Q, also a 10 prime. So 10 prime meaning that my prime doesn't divide P, which is not in N, okay? So I just study the map, the local map to V in N of the H1GV, okay? And of course, what I want to do is just to add some extra ramification. So I add my extra prime here, this prime. And just look at the localization map, but not on Q, but only in N. So in this case, we have equality. And now what is important is the next. So the next is what we call the BS here. And here I will call it the BSQ. Okay. And the next is not so important. Okay. So there is a natural map from here to here. And so what is the BS? So it's a little bit different from the BS I defined before. It's the alpha in K star such that the valuation of alpha is not zero modulo P for alpha V in S. So in certain sense, it's the S unit. You have to add the S unit. And the BSQ is the same as before, ES. Okay, no, sorry. It's not the B, it's the V. You have to take, because after that, we have to take the dual. It's the alpha in VS. But now, what I want that the alpha is the P power of KQ. And as before, in fact, we consider the dual. So the dual of BS is the VS, and the dual of VSQ is the BSQ. So it's the same, more or less the same as I did before. So in certain sense, this BS and the BSQ can be seen as Galois extension. And now, if you just look at what is the kernel of this map, the kernel of this map is easy. Huh? It's just the kernel of this map. Okay. Okay, so the kernel of this map here. So it's as I did before. Okay. Where is my? Oh, I lost my stylo. Okay. It's here. Okay, so the kernel of this map here is just generated by the Frobenius at Q, in fact. And the Frobenius, in fact. Because here, locally, what you want that the decomposition group is trivial, in fact, at Q. So it's exactly the decomposition group. And now here is the deal. Okay, just focus on the small square. Okay, so what is this square? Okay, so the product V in, okay, maybe I prefer to write the sum the V in S, in N of the H1GV. The map here is the dual, in fact, of VS modulo here, okay, dual. Here we have equality. And here you have this map. Right? And of course, here we have the Frobenius. At Q. This is the map. So remember, I say, okay, I want to find some extension over in my context here. what I say, I want to find some extension, f over k, cyclic extension with some local condition, such that when I make the compositon, at the end, there is no local obstruction to lift again. So I want to some specific global extension with some specific local condition. And the condition, of course, is the problem appear for the ramification. So in fact, what I want to, to, to do, so is that given some x here, some local specific condition. So I want that the x here, in the image of my map here, it was a global map, remember? And to be here in the image, it means to be in the kernel. And so maybe it's not in the kernel here, but what you want to do, that it's maybe you have to add some extra ramifications such that my x here is in the kernel of this map. And to be in the kernel in this map, it's easy. You just take the image of x here, okay? You take the denote by f, and it will be in the kernel if the Frobenius here is chosen such that the f of x is exactly also in the subspace generated by the Frobenius. So if you choose the q such that the Frobenius at q is exactly the fx, you win. It means that you have exactly a new extension, Z-mod P extension, f over k, such that locally you have exactly you want. That meaning that you can lift again your extension. This is the goal. Okay. So in fact, this strategy solve the problem. So in fact, prefer to write. So the difficulty for V in N. But now the problem that you add some extra ramification. You have, but you have we have a new ramification, a new prime, ramified prime, which is Q. The prime Q. Okay. So you solve the problem for all the N, but maybe for the Q you add some extra difficulty. Okay. And now, to be sure that you have no extra difficulty, it will work if Q, okay, you are safe, if Q is splitting in the extension you start in the construction, so it's splitting in my L over K here. And this is the main difficulty now because you have two opposite conditions a priori. So you want that Q is splitting in L over K, okay? And you want that Q, the Frobenius at Q, okay, is f of x, okay? In my governing field, so in my extension here. Okay. Okay. Get of K prime, P square root of V, it was my Vs like this, over K prime, okay? Which is a priori not zero, okay? So you have two conditions that can be opposite. You want Frobenius is trivial here and not trivial here. And this is why we say that we can have some difficulty if we have this situation. So K prime, it was K zeta P, okay? And so we start with L prime. And now, so we want that Q is splitting here, okay? And not splitting here. This is yeah. So splitting here. Okay, right like this. So you want that Q is splitting here. So sigma Q is the Frobenius is not zero here, but not zero. Okay. And so what you want also that the Frobenius here is zero. Of course, it can be incompatible, and this is the main difficulty. And we have saved when zeta p in the it's exactly the remark I made before. So when K prime is different from K, okay, when zeta p is not the base field, so the intersection is 1, it's trivial. Okay, so if this guy, this extension is trivial, so the intersection is one, so these two conditions are compatible, and then you are safe, and you can continue the process. I recall it that by adding some extra prime q, you solve the problem with the old ramification. Okay, you add some new ramification at q, but this new condition, in fact, is not difficult to save. So this is a strategy, and in fact, the proof of Shafarevich theorem, it's a beautiful proof, and it's exactly the same strategy. Huh? So what he said that he tried to see that in some situation, if the set of ramification is very huge, in fact, the Frobenius here is not in this part, but okay, the Frobenius here should be compatible with this part. So in this case, it is exactly in this part, but not in this part. This is the strategy of Shafarevich, huh? To be sure that the two conditions are compatible. But to do that, you need some a ton of ramification. Okay, so there is a notion of plan, I think. Maybe I have to mention the notion of plan that given by Ravi and also by Michael of local plan. It just okay. So we start with U, a P group. Okay, and a local plan is just given a place of K. It's just a map rho V from the absolute Galois group of KV to U. Okay, GB equal. This is the notion of local plan. In fact, you want that locally to control what is the map, in fact. And here the theorem we can prove is extension of the theorem of Chirstian. It was more or less in the paper with Michael and Farjid and Ravi, but it is written in this sense in the paper, joint work with Jan. So it's a joint paper with so myself, of course, but Minaj, Jan Minaj, Ravi Ramakrishna, and Tan, and Nguyen Tan. So we prove this one. So suppose that zeta p is not in the base field. Okay, so in the context of Church-Richard. So we start with two P group. Let U be a P group, so finite for me. And you start also with V is a normal subgroup of U. So we start also with an Galois extension. So I just maybe draw. So we start with this extension. By F over K, okay, with Galois group V over U. Such that, donc suppose we have this Galois extension, such that first F over K is unramified outside a set S of prime. Okay, so there's nothing to say. But what we want that for every place in S, every prime in S, we want that there is okay, the decomposition group denote dv bar, okay, which is a Galois group of fv over kv. So respect a local plan rho v from gv to u. Okay, so we are here in f modulo u, and so what yeah. And so what we want that is this local Galois group in the quotient in fact is the image of local plan. And so then we can lift. So there exists an extension FL, okay, such that here we have U. So here we have V. Okay, this is, and such that so locally we have that the decomposition group of of my extension such that for all V in S, the decomposition group of my new extension LV over KV respect my local plan, so respect the row V. And moreover, it's important, to do that, we can add some extra ramification. The new ramification also respect some local plan. Okay, I don't want to be more precise, but okay, this is the theorem. In fact, we use with Michael, but it was not right in this sense, but it was exactly this theorem. And now with this theorem, of course, there is many application. So the first application, it was the result with Michael Larsen, Fargid Agir. So it was the result with Agir, Larsen, and Ravi. So it's just to construct some extension where the image is a SLN, congruent subgroup with coefficient in ZP, and where the set of ramification is maybe surely infinite, but the ramification is 10. And this is okay, it was the lecture, see the lecture of Michael. So the second application, it was in the topic of Massey product. So this is a joint work with Minaj, so Yann, with Ravi and Dan. So at the same time, so we observe with Ravi that the construction with Michael and Fargid, in fact, can be translated in the Massey product situation. And it was the first thing to do. It was during my visit, my stay in Western, 2 months, thanks to invitation by Yann, to understand what is the philosophy of Massey product, and after that, to translate the question of Massey product in terms of inverse Galois problem. So just maybe I can recall some elementary thing. So we start with an integer n with at least 3. We denote by un plus 1 is a set of matrix, so unipotent matrix, where so you have 1, 0 below the diagonal, and where here the coefficients are in FP. And the size of the matrix is 1 plus 1 times n plus 1. It's not difficult to see that the center of the matrix, okay, the center of this matrix, of this group, 1 plus 1, is exactly the matrix where you have 1, 0, 1 everywhere with just a non-zero element, which is the last one. And also, it's not difficult to see that the Fratini subgroup of this, of course, un plus 1 is a P group, so the Fratini of un plus 1, just you have 1 here, 0, you put 0 on the upper diagonal and some coefficient above. So this is a Fratini subgroup of un plus 1. Okay, so of course, so I denote this guy by Wn plus 1, and if you look at un plus 1 modulo un plus 1, it's isomorphic to, can write like this, okay, like this, okay, meaning z mod p to the n, okay. This is why we start with un plus 1, because the key fact in the story, it's this guy, z mod p to the n, okay. So you lose 1 in one dimension. Okay, so you have 2 maps. So we have one maps. Okay, so maybe I can write this map. Okay, so we have this exact sequence. So the center, un plus 1, un plus 1 bar. Okay. Okay. Okay, and now we can just look at modulo the fratini. What's happened? You have to get to z mod p to the n. And I denote this map by phi, so and phi bar this map. Okay. In certain sense, you start with some matrix with some coefficient, and the reduction here, modulo the fratini, you just study, just keep the coefficient up above the diagonal. Okay. And now, so what is the strategy, the idea? So you start with n element, K1 in the H1. So you start with gamma profinite group. You start with element K1, Kn in the H1 of gamma with value in Z mod P. Okay. And I construct the map theta. I denote by K1, okay, to my group gamma to Z mod P. N. Just what I want to do. Just here, it's come from the map 5. Okay? So it's a homomorphic group. And there is a definition. Okay, so first thing, so the question of master product is just to see how we can lift a map. So if you start a map theta, okay, so you start with a map theta from this. And so okay, it's not completely correct what I write. It's not the 5 here, because I don't know if it exists. So you just said, okay, so S, Q1S, Q1S. And the question of master product, okay, so here maybe I can do a picture here. So you start with gamma here, okay, we start with a map like this, theta. And the master product is just to see if your map comes from the phi or the phi bar. So you say, okay, if the map here exists or if this map exists. Okay, so if this map exists here, we say that the master product associated to theta, so exist, is defined. And if this map exists, we say that the master product in fact vanishes. So it's just a question of lifting. You have a map from gamma to Z mod Pn, and you want to see if this map comes from the map through the UN+1 or the UN+1 bar. Okay. This is exactly a problem of Galois embedding of P-group. So it's clearly connected to Chirstian. In fact, maybe now I would follow some notation of Merkuriev. I like this notation. We have three sets of elements. So we have AN, BN, and CN. So the AN is the case where the theta, so theta is defined. Okay. In fact, theta in this case we write like this. So meaning that this map exists here. Okay. There is another set where says that theta vanishes. Okay. In this case, this map here is defined. And the CN is a case where, in fact, you have some condition between the homomorphism. So you have the key 1 cup product with key 2, which is in value in H2 is 0. So it's 0. And the key 2 cup key 3 is 0, etc. Blah, blah, blah. So K1 minus 1 cup K1, K1 is 0. Okay. So now it's not difficult to see that you have some inclusion. So you have AN is in BN, which is in CN. So this is classical. So AN is in BN because it's no, what I write. Okay, no, I make a mistake. Okay, it's here, no, it's okay, it's here, vanishes and define here. Okay, we have this inclusion, and we say that so definition. So gamma satisfy the unfold related to n, unfold Massey vanishing property, MVP, if we have an equal to bn. So it means that if your theta, for every theta, if for every theta, okay, you have a map here. So the Massey vanishing property is that if you have a map here, in fact, you can lift to un plus 1. Okay, and you have another property, gamma satisfy the n-fold strong Massey vanishing property if in fact an is bn is cn. Okay, it means that the necessary condition here is sufficient to lift this guy to un plus 1. So if you have a triviality of the coproduct, then you can lift this map here to un plus 1. So what are the main results in the topic? So first, the most general result is due to Scavia and Merkuriev. It's a very recent result. They prove that for any field, so K is a field, not necessarily number field. GK is the absolute Galois group of K. And you take gamma, this absolute Galois group of GK. They prove the theorem, they prove that A4 is equal to B4 for P is 2. Okay. The most general result. In the number theory setting, so we have a result of Hopkins and Wickel-Green. So they prove that A3 is equal to B3, okay, for number field, if K is a number field. And of course, gamma is the absolute Galois group of K. In fact, very recently, there is a very strong result due to Harpaz Wittenberg. So they prove that for every prime, so K is a number field. For every prime number, they prove that in every n greater than 3, they prove that an is equal to bn. So they prove that the Massey vanishing property for number field. Of course, gamma is also the absolute Galois group of K. This is paper in Duke. Yeah, and so with Jan, Ravi, and Tan, so it's a theorem we proved last year. And Tan, we prove very easily that if assumes that zeta p is not in the base field, okay, you take n as you want, okay, and you take gamma is the absolute Galois group of K with a number field. In fact, we can vary. We can take also gamma is a Galois group where there is only term ramification, but I prefer to simplify. So we prove that for this situation, we have an is bn is cn. So we prove the strong vanishing property. And also maybe I have to mention at this level that we know that when zeta p is in the base field, so maybe it's not right, this result in full generality, because for p is 2, in fact, we know that, and from some number field, we know that C4 is different from B4. So this is a counterexample due to Harpaz and Wittenberg. So, okay, for PS2, of course, zeta 2 is in the base field in this case. Okay, so in fact, we can do more. It was a joint work with Hamza and Lim. We can also apply this strategy to construct some Galois extension of Galois group. Donc, it was a work with Hamza. There was a joint common PhD student with Lim, with Minaj and Lim, just young Korean mathematician. So with this strategy, we can apply this strategy to construct just say a few words to construct some Galois extension of Galois group isomorphic to so you take UN, okay, with coefficient Z mod PR with few ramification. Okay, of course, it is in the number field setting. Yeah, because in fact, we should have in mind that if you want to construct this extension over a number field K or Q, okay, the set of ramification, if we follow the proof of Chirstian, so the size of the set of ramification is huge. It's a constant depending on the class group of K and the unit of K, plus something which depends of the N and the R. It's more or less NR to the square. So it's a huge set of ramification if you follow the strategy of Chirstian. And now, if we apply some construction like this, meaning if we use a Massey product, we can construct this kind of extension with very few ramification, meaning the size of ramification is more or less n. So, and yeah, it doesn't depend on R, in fact, and it's possible to do that. So maybe I just mention one thing, one theorem, I will stop here. Theorem. So assume, we assume two conjectures. So assume Leopold and Gra conjecture. I just mention what is Gra conjecture. Okay. So we take M with 1. Then for large P, so K is fixed. Then for large P, there exists a set N of time prime of size R2. R2 is a number of embedding complex, so of K, okay, such that the extension ramified in P, eventually in N, is maps onto U, so take 2R2 plus 2 Z mod P to the N. This is our result. And so what is the Gra conjecture? So the Gra conjecture says that for P large, the Galois group GSP, in fact, is free on R2 plus 1 generator. This is the Gra conjecture. So if we assume this conjecture, we can prove that this Galois group in the quotient of this Galois extension. So the set of ramification here is bounded by R2, in fact, and the set the place of both P. Okay, it doesn't depend on M. Okay, I stop here.